try to move you onto the board of directors.
Yeah, right.
All right, looks like Kelsey says the room is full, so I think we can get started. So I will do a brief introduction. So welcome everybody to the 2DCC webinar. It's our last one of the semester, and we are absolutely delighted to have Professor Mark Hersam from Northwestern here to give the seminar. So he is the Walter Murphy Professor of Material Science and Engineering, Director of the Materials Research Center, and Chair of the Material Science and Engineering Department at Northwestern. He has received a whole bunch of honors, including the Presidential Early Career Award for Scientists and Engineers and the MacArthur Fellowship and 8 Teacher of the Year awards, in addition to many, many other awards and honors. He's a fellow of MRS, ACS, ECS, AVS, a bunch of other societies, and is the editor of ACS Nano. So we are delighted to have Professor Hersam here. So please take it away whenever you're ready.
Okay, thank you, Stephanie. Thank you for the introduction and the invitation. Today I'm going to be talking about recent work in our lab in the area of mixed dimensional heterostructures in 2 contexts, electronic and energy technologies. Before we get into the details, let me give you some background information and introduce you to this concept of a mixed dimensional heterostructure. These heterostructures are built upon the family of low-dimensional nanoelectronic materials. This would include various low-dimensional forms of carbon, such as 2D graphene, which is a 1-atom thick sheet of sp2 bonded carbon. It would include carbon nanotubes, including single-walled carbon nanotubes, which you can imagine conceptually as being a rectangular sheet cut out of graphene rolled up into a cylinder. It also includes non-carbon-based low-dimensional nanomaterials. In the 2D space, that would include materials like hexagonal boron nitride, which is electrically insulating, molybdenum disulfide, which is a relatively wide bandgap, typically N-type doped semiconductor, phosphorine derived from black phosphorus, narrower bandgap, typically P-type doped. And we also look at the family of synthetic low-dimensional nanoelectronic materials, such as borphine, 2D phase of boron. We call it synthetic in the sense that you can't derive borphine from bulk boron by exfoliation, because bulk boron is not a layered van der Waals solid. You have to grow it directly from the bottom up using methods like molecular beam epitaxy. The point of the slide is to highlight that even with this small number of examples, we already have all electronic properties from metals to insulators and semiconductors in between. And as a result, if we could assemble these into heterostructures, we should be able to realize any and all electronic device functionality. And this is enabled by the fact that the bonding between these materials is van der Waals bonding, which means that you can create a heterostructure with an atomically sharp heterointerface without being constrained by epitaxial lattice matching. In other words, you can just layer these materials on top of one another with no further precautions being taken. And this has led to a proliferation of what I call 2D van der Waals heterostructures, such as graphene with hexagonal boron nitride, and we do that as well in our lab. But what we contend is that any passivated dangling bond-free surface interacts with another via van der Waals forces, and as a result, you can generalize this beyond 2D materials to the mixed dimensional case, where, for example, you could have 1D carbon nanotubes directly interface with 2D malate disulfide. The resulting heterostructure now has across its heterointerface a qualitative change in the nature of the electronic density of states, a qualitative change in the degree of screening. You can imagine excited states like excitons, where an electron resides on one side of the heterojunction, hole on the other, the composite excitonic wave function being neither 1D or 2D, but truly mixed dimensional in character. All of these new physics will imply new properties and ultimately new applications. In our lab, we pursue several different categories of applications. This includes neuromorphic or brain-like computing. We'll talk a bit about that today. It includes efforts in additive manufacturing, including printed electronics and batteries. We'll touch on that as well today. These materials and heterostructures can be used in quantum information science technologies like quantum computing and quantum communication. And also by exploiting magnetic ordering in low-dimensional direct bandgap semiconducting materials, you can look at the interplay between light, spin, and charge in what we call opto-spintronic heterostructures. These latter two, namely quantum and opto-spintronic, applications we will not cover today due to limited time, but these review articles can walk you through that content if you're interested. Instead, what I'd like to do is jump in and focus first on neuromorphic computing. So the reason our lab is motivated by neuromorphic computing is due to the rise of artificial intelligence. And what AI is doing is creating a tremendous stress on the grid, in that the energy consumption in training AI is now consuming as much energy as entire countries the size of Argentina. And I would contend that if we continue on this path, it's going to be completely unsustainable. Now, there may be solutions. For example, Microsoft has publicly announced that they're going to build gigawatt data centers, which are going to be powered by dedicated nuclear power plants. And if we're comfortable building lots and lots of nuclear power plants, then perhaps we can provide enough energy for what is going to be needed for next generation AI. But even in that scenario, these data centers are going to be dissipating lots of heat, and that's going to require hundreds of billions of gallons of cooling water annually, which I would contend is difficult to justify in a world where 2.7 billion people suffer from water scarcity. However you slice it, what we need is either to come up with radically different software solutions or different hardware platforms on which to run AI. In our lab, we focus on the latter strategy. And in particular, what we're going to look at is completely different ways of performing computing. And we're going to be inspired by biology, specifically the brain. And the reason is that the brain is orders of magnitude more efficient than a digital computer in the big data limit. One of the principal issues with the digital computer is its fundamental underlying architecture, the so-called von Neumann architecture, where you have spatially separated memory and microprocessor, which means that when you process large data, you have to move it back and forth between the two blocks, and that drives power consumption. In contrast, in the brain, memory and information processing are co-located in space, and this implies that neuromorphic computing has the potential to be orders of magnitude more efficient. Because this is difficult to implement using conventional silicon transistors, different devices are now under consideration. One of the most popular is the memristor. This is a resistor that remembers its voltage history. I think it's a quite interesting and in many ways suitable device for non-volatile memory and in some cases pattern recognition, but it has limited capabilities for higher order information processing or cognitive function. Additionally, and perhaps more fundamentally, memristors are typically two-terminal devices wired up in so-called crossbar arrays, which is fundamentally different than a biological neuronal network where neurons typically have hundreds, if not thousands or tens of thousands of synaptic interconnections. Hyperinterconnectivity is another characteristic that we'd like to mimic in neuromorphic computing. And so in our lab, we've really tried to rethink solid-state electronic devices in this context. And in particular, if we want to mimic biological neuronal networks, then we have very different constraints than a traditional transistor. For example, you'd like to efficiently achieve nonlinear voltage spiking, analogous to the action potentials in biological neurons. You'd like to be able to perform both memory and information processing at the same point in space. Can we, for example, combine a memristor and a transistor into one device? And can this all be done with multiple terminals to enable high levels of interconnectivity and reconfigurability to mimic that which is present in biological systems? So to go after those goals, we turn to mixed dimensional heterostructures. The first one I want to introduce is a 2D, 1D case where we have 2D N-type semiconducting molybdenum and 1D P-type single-walled carbon nanotubes. And if you layer these two materials together, you'll get a PN junction. And if you wire it up as a two-terminal device, you'll see a rectifying current voltage curve like you do with any other PN junction diode. The difference, though, is that this PN junction diode is made out of atomically thin materials, which means that the thickness of the device is thinner than the screening length of electric fields, which implies that this is a highly gateable PN junction, one where you can electrostatically modulate the carrier concentration just by applying voltages to the bottom and or top gate. Moreover, because it's mixed dimensional, the degree of screening is qualitatively different. It's much lower on the 1D side than the 2D side, and that asymmetry in screening gives you further tunability over the nonlinear current voltage characteristics. Here are some examples of the IV curves you get from that device. You can see that it looks much like a Gaussian response or an anti-ambipolar response. By that I mean a flipped over version of the transfer curve of an ambipolar transistor. The way it works is that when you're at large negative gate voltage, you fully depleted the N side of the junction and therefore the device is off. When you're at high positive gate voltage, you fully deplete the P side of the junction, the device is off. Only at low gate voltage is the device on. If you then exploit the fact that this is a 4-terminal device and you adjust the voltages on those 4 terminals suitably, you can tune all the hyperparameters of a Gaussian, including the peak height, the peak position, and the peak width. And once you achieve that level of tunability in the nonlinear current voltage response, you can then build artificial neurons by adding a relatively small number of additional conventional circuit elements. For example, if we take one of these Gaussian van der Waals heterojunctions, connect to it a few resistors, capacitors, and conventional transistors, and input into this circuit a synaptic current, then the voltage at the output as a function of time will spike, very much analogous to the action potential of a biological neuron. Of course, the difference with this artificial neuron is that you can tune the details of the spiking response just by changing the voltages you apply to the Gaussian heterojunction. And that will allow us to achieve a dense set of functionality in a very small footprint compared to implementations using conventional silicon transistors. Fast forward a couple of years in our lab, we began digging into the details of this device. And as I alluded to before, the asymmetry in screening is critical to tuning the nonlinear current voltage characteristic. And as a result, if you now specifically engineer for that asymmetry, which you can do by changing the carbon nanotube concentration and or the degree of overlap between the P and N sides of your heterojunction, that allows you now to not only get the tunable Gaussian response I already showed you, but also for the exact same device, under different biasing conditions, you can get a tunable sigmoidal characteristic or a linear combination of the two, which is referred to as a mixed kernel response. And this is of interest for machine learning because mixed kernels are the basis of efficient pattern recognition using support vector machine. And as a result, we can use these so-called mixed kernel heterojunctions to enable highly hardware efficient support vector machines for doing machine learning classification directly in hardware. The example I'm showing you here is one where we're looking at electrocardiogram data. This is basically measuring your heartbeat, utilizing, for example, a wearable. And what we want to detect from this complicated data set is, do you have an arrhythmia or an irregular heartbeat? And by utilizing support vector machine with a personalized mixed kernel, by that I mean tuning the hyperparameters and mixing ratios between the Gaussian and the sigmoid, you can achieve very high levels of accuracy, which is personalized to each patient. This means that you can have customization without having to change the hardware, just changing the voltages applied to the hardware. Additionally, this is done using 100-fold fewer devices than if you were to implement this in silicon CMOS, which of course lowers power consumption, and implies that you can now do this in hardware machine learning directly on the wearable, which not only has a power consumption advantage, but also a privacy advantage in that your sensitive personal health data no longer needs to be sent to the cloud to do machine learning classification. It can all be done under your control on your personal wearable device. A related device that we've been working on is a so-called interfacial junction transistor. This is actually not mixed dimensional. It's just a 2D van der Waals heterojunction between graphene and MOS2. It looks like a very simple device, but what we're exploiting here is the fact that when you have van der Waals heterojunctions, you typically will have redistribution of charge, and in particular, charge transfer doping. In this case, driving the MOS2 under the graphene to be more lightly doped than outside of the graphene. And when you have a spatially varying doping profile from high to low to high doping, this is quite analogous to a conventional bipolar junction transistor. And indeed, you can operate this device in a regime where it looks a lot like a BJT with current gains and beta values in the order of a few hundred. But the difference between this device and a conventional BJT is that it's atomically thin and therefore highly gateable. And as a result, you can use the gate to get a field effect on top of the bipolar junction response. So it's a hybrid field effect bipolar junction transistor. Additionally, because it's a planar device, there's nothing stopping you from putting additional gate contacts to the device. In this case, we have two graphene contacts directly in contact with the MOS2. Additionally, we have dielectrics on top and bottom of the device with additional conventional gates present, giving us now a 6-terminal device, which allows us to achieve even greater control over the nonlinear current voltage characteristics. In addition to getting a tunable Gaussian, which I already showed you for the mixed kernel heterojunction, we can also get a so-called pi-like response. There's going to be a range of gate voltages where you see no tuning of the current flow through the device. Or you can create mixtures between Gaussian and pi, and it turns out that mixed Gaussian pi responses enable efficient implementation of fuzzy logic hardware and fuzzy neural networks, which are quite suitable for applications like image segmentation. The next device I want to introduce is one that at first glance looks like it's a 2-dimensional device, but we view it as a mixed dimensional heterostructure. And the reason is that it's made out of polycrystalline molybdisulfide. And if you think about polycrystalline 2D material, the grain boundaries become 1-dimensional. And it turns out that the properties along the grain boundary are qualitatively different than in the pristine grains. And as a result, you get a mixed dimensional response from a single material. And in particular, the mixed dimensional response that's most useful in this device is the fact that defects in the MOS2, such as sulfur vacancies, have a dramatically reduced barrier to motion along the grain boundaries. This is what material scientists would call short circuit diffusion. The reason that's relevant is that the vacancies in MOS2 are the N-type dopants. And if you have a low barrier to moving the vacancies around, that means with modest excitation, such as a relatively small lateral electric field, you can drive vacancy motion through the channel, thereby reconfiguring the doping profile of your device. And in particular, if you use Schottky contacts, when you linearly change the doping under a Schottky contact, you get an exponential change in the charge injection, which means that you can get very strong non-volatile changes in the conductance of the device. In other words, you get a memristive response. This is a 2D or mixed D version of a memristor. But again, unlike a conventional memristor, this is one which is atomically thin and therefore easily gated. And as a result, you can combine the functionality of a 2-terminal memristor with the gate tunability of a transistor, or we call it a MEM transistor for short. These were some of the first MEM transistor devices we produced. They show the qualitative features of the device. And in particular, in the 2-terminal current voltage response, you see a large memristive hysteretic loop. You will note that when you go to negative bias, the hysteretic loop is attenuated, and that asymmetry can be traced back to the fact that this is a device where all the action is happening at the Schottky contact, which will typically have some rectification character to it. On the left, I'm showing you a series of those 2-terminal IV curves on a log linear scale at different gate biases. And you can see due to the log scale that we're tuning the conductance state of the device by 6 orders of magnitude, like a traditional transistor. So this is the transistor action on top of the memristor action. This device, like the interfacial junction transistor I showed you, is also lateral, which means you can put more contacts into the channel region if you wish. In this case, we have 6 contacts in the channel, in addition to the gate being the 7th contact. If we apply a voltage between contacts 5 and 6, we can get vacancy motion in that direction, which of course, as I just showed you, will modify the current flow in that direction, but it will also modify the current flow in the orthogonal direction, for example, between contacts 2 and 4. So in this case, I'm plotting the current voltage curve between contacts 2 and 4 as a function of voltage pulses between contacts 5 and 6. And as you can see, we're getting non-volatile changes in the conductance of the device in the orthogonal direction to the voltage pulses being applied. This is referred to as a heterosynaptic response. It is one that's very well known in neuroscience and now can be implemented in solid-state electronics. Moreover, and as I alluded to at the beginning of the talk, this is a multi-terminal device which presents options for high levels of interconnectivity to better mimic biological neuronal networks. This device, like the others I've shown you, is atomically thin, and consequently you can gate it from the top and or the bottom. In this case, we're doing both, a dual-gated MEM transistor. This has some practical advantages. If you want to wire this up into a crossbar array, which is certainly the most popular architecture currently for neuromorphic computing, what the second gate gives you is the ability to address uniquely one point in the crossbar without having crosstalk or sneak currents between the different nodes, which is a fundamental problem with memristive crossbar arrays. Additionally, when you have two gates, you get more tunability over the memristive or so-called synaptic response. For example, you can use the two gates to get a linear and symmetric synaptic response, which is quite useful for some pattern recognition algorithms. Now, the whole concept here is that this device is exploiting vacancy motion via grain boundaries, which means that if you tailor or control the defect concentration and or the grain boundary structure, that should have a predictable change on the current voltage response. And that's illustrated here by growing the MOS2 now on sapphire as opposed to silicon dioxide in the previous example that I showed you. And when you grow on sapphire, you get a less defective MOS2, fewer grain boundaries, reduced vacancy concentration, the net effect being that the memristive loop is attenuated. In other words, the transistor action is more dominant with this type of MOS2. And when you have a more dominant transistor action, that means you get more gate tunability over the memristive or synaptic response. In this case, what I'm showing you is the conductance change in the device as a function of voltage pulses. All the pulses are going to be the exact same polarity and duration. Typically in memristors, to move from a growing conductance or potentiation to a reducing conductance or depression, you have to change the polarity of the pulse. In this case, the pulse is constant. All we're going to change is the voltage applied to the gate. And as you can see, we can tune happily between potentiation, depression, or no synaptic response just by changing the gate voltage. The ability to switch between learning or potentiation and forgetting or depression with unipolar pulsing is biorealistic in that the action potential in biological neuronal networks is always unipolar. And that ability to be more biorealistic means that we can now go after more sophisticated types of learning, including so-called continuous learning. What is continuous learning? Well, to explain it, it's perhaps best to talk about a conventional neural network. And in a conventional neural network, what you do is you train the neural network on a given task. In this case, the task is to recognize the digits 1 and 0. And then if you want to train it on a new task, like to learn two different digits like 3 and 4, you then have to retrain. And in the process of that retraining, you forget the knowledge gained from the initial training. This is known as catastrophic forgetting, and it leads to inefficiencies in doing multitask learning in neural networks. In contrast with the increased gate control of these MEM transistors, we can now tune the neural network on demand to either learn or forget at the individual node level just by changing the gate voltage. And that allows you now to retain the learning of the previous task, in this case, recognizing digits 1 and 0, while learning the new task, in this case, learning the digits 3 and 4, where you get high accuracy for both tasks with minimal additional costs in the training. And as a result, you circumvent traditional trade-offs between accuracy and resource allocation. The last thing I'll say about this topic is that every device I've shown you for MEM transistors had very large voltages. And the reason was that in the proof of concept stage of this effort, we used relatively large devices, i.e. photolithography. More recently, though, we've begun looking at scaling of these devices down to the deep submicron limit using e-beam lithography. And as you might expect, the voltages should be lower if the device continues to work. And happily, it does continue to work. We now see the same hybrid memristor transistor response I showed you before, except now you'll see the voltages, instead of being tens of volts, are single volts. So now we have sub-volt operation. And the current levels also can get down to the nanoamp scales to the overall power dissipation is nanowatt scale, making it comparable to traditional silicon technology. So the scaling looks quite favorable, and that of course leads to higher density and lower overall power consumption. The last device I want to introduce is one that's called a Moiré synaptic transistor. This is going to use a different type of physics, so-called Moiré physics. Moiré physics arises when you have two different 2D materials that are lattice mismatched. For example, bilayer graphene and hexagonal boron nitride. They have the same crystal structure, but their lattice constant is different, which means that the perfect registry between atoms will occur on a larger length scale than the atomic scale. This is a so-called Moiré pattern. That Moiré pattern will introduce a secondary periodic potential on top of the atomic periodic potential. That is the so-called Moiré potential, which in this particular case is sufficiently deep that it's greater than KT at room temperature. And as a result, the electrons in the top layer of this bilayer graphene structure are going to be localized in space. In other words, they don't move. In contrast, the bottom hexagonal boron nitride, we're going to rotate compared to the bilayer graphene. And when you rotate it, you decrease the length of the Moiré potential, you decrease the depth of the Moiré potential to the point where at room temperature, the electrons in the bottom layer are effectively free. So what this device has is two layers of graphene separated by 3 angstroms in space. In one layer, the electrons move, and the other layers, they don't. That's, of course, a very unusual circumstance and implies that you get unusual synaptic responses. That's illustrated here. So what I'm showing you is a plot in color of the resistance of the device, or the inverse of the conductance. And then on the x-axis, I'm varying the bottom gate voltage. On the y-axis, I'm varying the top gate voltage. So let's just look at the bottom gate at first. If we look along the bottom gate voltage axis, we see that there's going to be a peak in the resistance or a dip in the conductance, which is characteristic of the ambipolar response of a traditional graphene transistor. So everything with respect to the bottom gate is normal. In contrast with the top gate, when you start changing its voltage, you see no change in the IV curve. That continues until you get to some critical point, and then you begin to see a shifting of the Dirac point, which is what you'd expect for a dual-gated graphene transistor. So the unusual behavior is what's happening until you start to see the shifting. And the reason you don't see shifting initially is that since the top gate is near the top layer of the graphene, you're changing the carrier concentration in the top layer where the electrons are immobile, and therefore they have no effect on the IV curve. It is only when you fully populate or deplete that top layer of the graphene that the top gate has an effect on the bottom layer and then shifts the Dirac point. And this is true in both directions. When you're now returning down in gate voltage, initially you extract carriers from the immobile region, getting no change, and then you shift into the tuned Dirac point regime. The net effect is that you get an asymmetric ratcheting behavior that will underlie the unique synaptic response of this device. And that's shown here. So what I'm showing you is the degree of depression or reduction in conductance or potentiation increase in conductance as a function of the bottom gate. And as you can see, as a function of the bottom gate, you switch between depression to potentiation. That in and of itself is not new. I just showed you can do that utilizing the MEM transistor. But what's different about this device is that we can use the second gate, namely the top gate, to shift where that transition occurs between depression and potentiation. And the ability to tune the LTD-LTP transition is something that's well known in neuroscience to underlie what is known as input-specific adaptation. And because we can now do this in hardware, we can realize that sophisticated cognitive function in neuromorphic computing. And that's illustrated here. In particular, when you have a tunable transition between depression and potentiation, you can achieve the ability to adapt your neural network to different input conditions. And this is quite useful in a lot of contexts. The one which is perhaps most easy to understand is self-driving vehicles. In self-driving vehicles, you will typically train the vehicle's neural network under a certain set of conditions, say a sunny day. And as long as it's sunny out, the neural network is going to give you good guidance for your self-driving vehicle. But if the conditions change, like it gets dark outside or it becomes foggy, you have to retrain the neural network because it can't adapt to the conditions. In contrast, when you have the ability to tune this transition, you can induce your neural network to adapt to the changing conditions without having to retrain. That gives you a substantial improvement in hardware and energy efficiency, one which is commonplace in biological systems and now possible to implement in solid-state electronics. Okay, so let's move on. In addition to neuromorphic computing, today I wanted to tell you a little bit about the work in our lab in additive manufacturing with a specific focus on energy technologies such as batteries. For this aspect, we're talking about technologies that are very widely deployed and where you need to have lots of material. Unlike high performance electronics where you don't need that much material, if you're talking about batteries, for example, for an electric vehicle, you need to have a lot of your nanomaterial. And as a result, we're gonna have to produce it using scalable methods, particularly using solution-based methodologies. And we've been doing this in our lab for many years, including through our company NanoIntegris, which commercialized semiconducting carbon nanotube inks, all solution process back in 2007. Nowadays, we also do printable 2D material inks, which are all available commercially from Millipore Sigma. Because we can produce huge quantities of these electronic grade nanomaterials, we then ask the question, can we go after large scale technologies like batteries? And in what context would these materials be useful? For that, let me quickly walk you through how a lithium-ion battery works. There's two electrodes, an anode and a cathode. They're separated by a separator to ensure no shorting between the two electrodes. There's an electrolyte, typically liquid, which will facilitate ion motion between the anode and cathode when you're doing charge and discharge. And you can, in principle, use these materials to go after any of those components of the battery, but what caught our eye when we were looking at this initially was none of those components, but rather these two layers here, the so-called solid electrolyte interface, which is a layer that builds up due to unwanted chemistry at the electrode-electrolyte interface, and this will build up and grow as the battery is cycled. And the buildup of the SEI is one of the reasons that you see capacity fade in a rechargeable lithium-ion battery. The reason we're attracted to this is that this looks like a very thin layer, very much like a 2D material, and as a result, perhaps we could come up with an artificial SEI that would allow you to have more stable cycling. And so we went to the lab and started thinking about how we would do this. The first thing you got to figure out is how can you encapsulate all of the particles, the active material particles in a battery electrode using 2D materials. We did this using solution-based processing. We took one of our graphene inks, we added to it an active cathode material, namely lithium manganese oxide. And then we tailored the drying and subsequent annealing conditions to drive conformal wrapping of each and every particle in your composite electrode with a few layer graphene coating. This now will present a physical barrier between the electrode and the electrolyte that will hopefully mitigate unwanted chemistry at that interface. And in particular, we chose lithium manganese oxide because it has a very famous failure mode, and that is manganese dissolution into the electrolyte. And that manifests itself as capacity fade, both in half cell and even more significantly in the full cell. And it's worse in the full cell because the leached manganese from the cathode will go across the electrolyte to the anode and corrupt it as well. So in a full cell battery, both the cathode and the anode are being corrupted by manganese dissolution. And this is a problem. This is why lithium manganese oxide is rarely used commercially because it has fast capacity fade. However, with the graphene barrier, we suppress manganese dissolution and get much more stable cycling. Additionally, graphene is electrically conductive, unlike the insulating SEI that builds up upon cycling in a traditional lithium-ion battery. And that electrically conductive coating means you lower the impedance of the battery, which means that you can get higher cycling rate performance. And that's shown here. In purple, we're seeing a traditional battery. And when you're at a high rate, where 1C means cycling in an hour, 20C means cycling in 3 minutes, you can see the 3-minute cycling leads to very far short of the capacity you get in the slow charge discharge limit. In contrast, in green, we have the graphene encapsulated case. This is clearly achieving much higher capacity, even at very high cycling rate. So this all looks quite good. We thought about taking this commercial at that time, but when we dug into the cost of doing this, we learned that the amount of graphene required to get conformal coating of all the surfaces was way too high. And the reason that's true is that we were just randomly mixing the two components together as opposed to intentionally driving the graphene to coat only at the surface of the cathode particles. So we had to figure out how to do that. And the way we did it was to use a trick from soft matter processing, namely Pickering emulsion processing. In Pickering emulsions, what you have are two immiscible solvents, in this case, acetonitrile and hexane. And if you agitate these two immiscible solvents, you'll form droplets of hexane in the acetonitrile exterior. The problem is that that emulsion is not stable. And so if it sits for any reasonable period of time, it will phase separate like oil and water. Unless you add another component to the dispersion, and in particular, graphene will stabilize the interface between the hexane and the acetonitrile, which means that we can get a stable emulsion, a so-called Pickering emulsion, and it implies that we have graphene now at the surface of all of our hexane droplets. We then exploit the fact that our active material particles disperse selectively in hexane, therefore they are recruited naturally to the interior of the droplets. Again, remember there's graphene on the exterior of the droplet. We then exploit fractional distillation, the fact that hexane is a lower boiling point than acetonitrile, meaning when you heat this up, the hexane boils off first. That leads to the graphene coating collapsing and conformally coating each and every particle in your dispersion. This is considerably more efficient, approximately an order of magnitude more efficient in terms of the amount of graphene required to coat conformally all the surfaces in your complex composite cathode. And when you get now down to the 0.5 weight % limit for the carbon in your electrode, this becomes cost competitive. It also implies that you can minimize, if not eliminate, the typical conductive additive in a battery, namely carbon black. This instead is a conformal conductive additive, which takes up essentially no space. And as a result, not only do you get a gain in the gravimetric capacity, but also the volumetric capacity approaching theoretical limits at the electrode scale. This is all done using scalable manufacturing and is the basis of our relatively new company, Valexion, which is taking this to the electric vehicle market. This not only allows you to take conventional battery materials such as NMC, which is commonly used by a lot of electric vehicle manufacturers today. It not only makes those materials better, but also allows you to go after materials that have not yet made it to market, such as lithium nickel oxide. This material is desirable because it's higher capacity than what's currently used in industrial lithium-ion batteries, and it has no cobalt in it, which is desirable because cobalt has some serious supply chain issues. The problem with lithium nickel oxide, and the reason it never made it or has not yet made it commercially, is that when you go to high states of charge, you drive oxygen evolution from the lithium nickel oxide. And you can see that clearly in mass spec with oxygen being evolved from the electrode. And you can guess if you start to lose oxygen from your electrode, that leads to all sorts of problems that ultimately leads to capacity fade. In contrast with the conformal graphene coating, it acts almost like a hermetic seal. It presents a large barrier to oxygen out diffusion. And as a result, you suppress the oxygen evolution. You see no evidence of it in mass spec, and correspondingly, you see much higher cycling performance. For completeness, I will note that this same approach can be applied to the anode. It works best for oxide-based anodes like the titanate family, or in this case, lithium titanium silicon oxide. These anodes are rarely used commercially, particularly because they have low electrical conductivity and therefore poor rate performance. But once you put a conformal conductive coating, namely graphene, on top of these otherwise insulating anodes, they now become quite conductive. And as a result, you get high rate performance and therefore achieve sufficient power densities to make them commercially viable. Okay, so we talked a bit about how we can use graphene as a barrier on both the cathode and the anode. The last frontier in the battery then would be the electrolyte itself. And in the most recent work in our lab, we've decided to take on the electrolyte. In a traditional battery, the electrolyte is a liquid, so there's not really a place for nanomaterials. But if we think about next generation batteries, which will be all solid state, then perhaps nanomaterials could be used as an alternative solid state electrolyte. And this would, of course, be of high interest, particularly from a safety point of view, because it's the liquid electrolytes in traditional lithium-ion batteries that present the flammability hazard, which is the most catastrophic failure of a lithium-ion battery. In contrast, if you get rid of the liquid and only use solvents, then of course you dramatically improve the safety of the battery. Of course, this is not a new idea. People have been trying to realize solid-state batteries for several years now, and some of the candidate materials are shown here. I'm not going to walk you through them in any detail other than to highlight that they all have some issue, like high interfacial resistance, poor ionic conductivity, difficult to process, high cost, and so on. And as a result, none of these has really made it, or at least are not widely deployed yet in a commercial setting. And as a result, it seems like there is opportunity to develop new types of solid-state electrolytes. And in particular, we were drawn to this family of quasi-solid electrolytes known as ionogels, where you blend a liquid electrolyte, such as an ionic liquid, with a solid matrix. And if you had enough solid matrix, you can drive gelation to create a quasi-solid material. And this is typically done using polymers as a solid matrix. The problem with using polymers as a solid matrix is that the gel now becomes very soft. Its solid-like character is compromised, and as a result, you still have a lot of the issues you have with traditional liquid electrolytes, including the need for a separator to prevent shorting between the two electrodes. In contrast, if we replace polymers with a material like hexagonal boron nitride, which is more ceramic-like in character, you can get dramatically improved mechanical properties while having all the other desirable attributes of a solid-state electrolyte, including high electrical insulating character and high thermal and chemical stability. Okay, so what we do is we take our hexagonal boron nitride, all solution processed, we blend it with ionic liquids. By tailoring the surface chemistry of the HBN to drive strong interaction with the ionic liquid, we can get strong gelation. And we can do that in a manner where we get now enhancement in the mechanical properties or the stiffness by a couple of orders of magnitude compared to conventional polymer ionogels. And this is all done without compromising the ionic conductivity, meaning it should be suitable for use in batteries. If we take that ionogel electrolyte and we make a battery out of it, we find that it cycles nicely and actually leads to even higher cycling than the liquid analog of that battery. And that's shown here. If we use a high voltage cathode like lithium nickel manganese oxide, which can go up to 5 volts, we can see that in those high potential conditions, we get very rapid capacity fade using liquid electrolytes. In contrast to the gel, we see much more stable cycling, and as a result, we are enhancing the electrochemical properties. If we now take those gels and we make full cell batteries out of them, we see that they cycle very nicely with very low fade, very high coulombic efficiencies. Because hexagonal boron nitride and ionic liquids are both very thermally stable, up to and above 300 degrees Celsius, you can operate these batteries at high temperature, as high as 175 degrees C. In fact, what's limiting you is not the electrolyte, but actually the electrodes themselves. And as a result, you could probably go higher if you start working on the electrodes' refractory nature. So that all looks quite good, but there's still a problem. And the problem is that liquid electrolytes, particularly ionic liquid-based liquid electrolytes, have finite electrochemical stability windows. I already showed you that they're good in the high potential limit, but I did not show that they work well in the low potential limit, and I didn't show you that because they don't work below 1 volt, which is a problem because that limits the types of anodes that you can use. The anode that everyone wants to use is graphite, because that's used in basically every battery today. So then you might say, well, change your ionic liquid to one that works at low potentials. And you can do that. The problem is that the low potential ionic liquid options are now limited in their high potential performance. And what matters ultimately in a battery is the delta V, the change in voltage. So both the low potential and high potential have the same delta V of 4 volts. And so you gain nothing by switching to the low potential electrolyte alone. However, if you have a quasi-solid electrolyte like we do with our ionogels, now you can imagine getting the best of both worlds, where you put the low potential ionogel on the anode, the high potential on the cathode. You can sandwich this together into a layered heterostructure electrolyte. And because they're quasi-solids, you get minimal intermixing at the heterointerface. And as a result, where you have them both present, the voltage is going to be midpoint between the two ends of the spectrum where they're both stable, thereby allowing you to use the full range of voltage that you have in a commercial battery. And in particular, if you make one of these cells using graphite as the anode, nickel-rich NMC as the cathode, you can now cycle over the full range and get very high cycling stability and high Coulombic efficiency. If instead you had done this just with liquids or a blend of the two ionic liquids, then they're both touching both cathodes, they're both undergoing unwanted degradation, and you see very fast capacity fade. So this type of solid-state electrolyte allows us now to go after new concepts in solid-state batteries and get high energy densities. There's one final problem, and that is the way my students made our first ionogels was to take hexagonal boron nitride powder, add ionic liquid, and then grind it with a mortar and pestle to make a gel, and then use a spatula to slap it between electrodes and make a coin cell battery, which is okay for an academic demonstration, but certainly is not a scalable manufacturing method. So we had to take on that challenge, and the way we solved it was to add a diluent solvent, namely DMF. That allows us now to create a precursor slurry whose viscosity is tuned to match that of traditional slot die coating or blade coating, which is already used in the battery industry. You then perform that slot die or blade coating to deposit your ionogel with the solvent, and then via just drying of the solvent, you drive strong gelation, creating your ionogel now in a scalable manner. This works quite nicely. You can go to large areas trivially. Because it goes down wet, you can conform your gel, even though its final state is very stiff. When it goes down, it's soft because it's still having large diluent solvent concentration. And as what you can conform to irregular surfaces that are inevitable in batteries, and then drive gelation to get all the desirable mechanical and electrochemical properties. This works quite well. You can get very nice cycling performance using lithium metal batteries, where this is now suppressing lithium dendrite growth, allowing us to get both high cycling and high current density. I'll note for completeness that you can tailor the viscosity of these inks on demand to make it compatible with your favorite additive manufacturing methods, such as screen printing. Here we use a different solvent, ethyl lactate, to make this less viscous than we would need in the blade coating case. This allows us now to make fully additive manufactured or screen printed lithium-ion batteries where all components, including the electrolyte, are screen printed. This is quite useful for things such as flexible or wearable electronics. And for completeness, I will note that these electrolytes can be used in other contexts. For example, micro supercapacitors. And just like I showed you with batteries, because the ionogel is thermally stable, you can run these micro supercapacitors up to high temperatures on the order of 180 degrees C, still getting beautiful current voltage characteristics. And additionally, because they are printed using screen printing, you can do this at large area to make arrays of supercapacitors. In this case, we have it wired up in both a series and parallel configuration, allowing us to achieve maximal current and voltage concurrently to go after higher power applications. So with that, I see I'm out of time. I'll quickly summarize the 2 points I tried to make today. The first is that electrostatic control and mixed dimensional heterojunctions enable diverse neuromorphic computing functionality. And secondly, solution processed low dimensional materials can be integrated into large volume applications such as solid state energy storage devices, and in particular allow you to improve stability and safety. With that, I will conclude by acknowledging my research group at Northwestern University, thank all the funding agencies for supporting the work in my lab, and thank all of you for your kind attention. I'm happy to take any questions.
All right, thank you so much. We have a few minutes for questions. So if there are online questions, you can raise your hand, or Kelsey can let me know if there's in-person questions. Go ahead.
Thank you for your great talk. So I have a question regarding the MI2 memorator. So we all know the green boundary is like a kind of defect of MS2. So how's the endurance of the device?
Yeah, so the grain boundary is going to stay constant. The vacancies are going to move along the grain boundary, and that's quite reversible process. So the endurance is quite good. We've extrapolated out to the years sort of time scale, and you can cycle this on the millisecond time scale for years. So I think it's sufficiently high endurance for non-volatile memory applications if you want to go that route. Although personally, I don't find non-volatile memory to be the real opportunity here. It's more the gate tunability of the synaptic response, allowing you to do more sophisticated AI than a traditional memristor.
So actually, we have some W2 sample with like similar grain boundary, and we tried to measure the memorial response, and like we just got some preliminary results, but like it will change every run. So do you think there are any difference between the W2 and the M2 grain boundary?
The barrier to motion on MOS2 is lower, so I think you get more facile motion. The thing I will stress is that to get uniformity from device to device, you want to have multiple grain boundaries per device. If you have a single grain boundary device, which is actually where this project all started about 10 years ago, we saw a lot of variability from device to device. By having many grain boundaries per device, then that variability at the single grain boundary level gets averaged out at the device scale and gives you much higher uniformity. So that might be part of the issue. We haven't pushed tungsten disulfide in any serious way. So it might just be harder in general. That I can't comment on, but I would say having small grains and high sulfur vacancy concentration should improve the uniformity.
Okay, thank you so much.
Any other questions in the room?
So it looks like we have a question in the chat. So the chat question says, thank you for a great talk. Wondering on the part 1 of your talk on neuromorphic computing, in your opinion, which material is really the most promising for such an application, since metal oxides and carbons is also of interest to researchers?
Yeah. So I think if you want to make a non-volatile memory or just a traditional memristive crossbar array, MOS2 has no obvious advantage. The other options like metal oxides are much more mature, and I don't think this material is going to beat them at their game. But where the 2D version, the MOS2 version of the memristor has competitive advantage, in my opinion, is the gate tunability of the response. And again, that allows you to do things you can't do, or at least you can't efficiently do using the 2-terminal memristor. It also has some sort of architectural advantages that I briefly alluded to, namely in a crossbar array with traditional memristors, you get crosstalk or sneak currents between the nodes in the crossbar, which means that you need another circuit element like a transistor or a diode, which increases the footprint of the device. So by eliminating that with the gate tunability and gate addressability of the MEM transistor, you can go to higher device density. To me, that's sort of a secondary advantage, but it is another one you gain from this compared to a 2-terminal memristor.
Thank you.
Thank you. Any other questions from anybody?
Doesn't look like it.
All right, well, let's all thank Professor Hersam again for a very interesting talk. And that's the last 2D seminar for the semester. So we'll see you all in the fall.
All right, have a good summer, everyone.
Thank you.
Thank you.
Thank you.